Hi everyone, my name is Daehyeok Kim. I'm a PhD student at CMU. In this talk, I'll be telling you about how to build fault-tolerant stateful in-switch applications with our system called RedPlane. This is a joint work with Jacob Nelson and Dan Ports from Microsoft and my advisors Vyas, Sekar, and Srinivasan from CMU. To give you a context of this work, in traditional networks, switches are just a stateless packet processor that forwards packets based on simple match action rules. In contrast, in today's networks with programmable data planes, network switches become a stateful in-network compute machine that can perform some stateful actions. A key enabler for this is the recent advance of programmable switching ASICs such as Intel's Tofino chip, which can process a few billion packets per second at line rate while executing some stateful operations for each packet. By leveraging this new technology, recently there have been many works that demonstrate the feasibility of various applications running on switches, which are called in-switch applications. This includes conventional network functions such as load balancer and NAT, and more innovating use cases such as network monitoring and accelerating distributed systems. While many recent works have shown the performance benefits of in-switch applications, there is one important problem that has not been explored well, which is handling switch failures. So what happens to the applications when a switch fails? Let's take a look at an in-switch NAT as an example. Suppose that the NAT has been deployed at two switches in the network. Initially, this red flow is routed to the NAT 1. Now, the switch running the NAT 1 fails. Since today's networks are typically engineered to mask such a failure by providing redundant path, the upstream switch can route the flow to an alternative switch. Packets now arrives at the NAT 2, but since this NAT instance does not have the flow state, packets cannot be processed and the connection will be broken. While I use the NAT as an example here, switch failures can lead to incorrect behaviors of various stateful applications, including other stateful network functions. Indeed, recent measurement studies in production networks have shown that switch failures are common in practice. So, how to make in-switch applications tolerant to switch failures? Since fault tolerance is a well-studied area in traditional server-based systems, we've looked at existing fault tolerance mechanisms to see if we can apply them to the in-switch applications. In this example, there are two switches and one is the backup for the other. We first try to adapt checkpoint recovery mechanism through the control plane and the external state store. When a packet arrives and updates the state, it periodically takes a snapshot and transfers it to the external state store, and populates the recorded snapshot for recovery when a switch fails. To achieve a consistent snapshot, data plane execution must be paused and packets need to be buffered during the snapshot period. However, due to the lack of such a capability and limited data to control plane bandwidth in the switch architecture, this is impractical today. We also consider a state machine replication approach using chain replication in the data plane. Packets are forwarded through a sequence of switches, each of which updates its state and forwards the packet to the next switch in the chain. However, the state updates are delivered over an unreliable channel, so these messages can be lost or reordered, violating correctness. And using one switch to replicate another switch's state makes poor use of limited switch memory. It may also require changes to the routing policy, since a packet needs to be routed to a specific switch in the chain, depending on whether the packet updates or reads the state. So this exercise shows that existing approaches designed for server-based systems cannot be directly applied to in-switch applications, and motivates us to design a new solution. Based on the key takeaways from this exercise, we designed RedPlane, which provides a fault-tolerant state store abstraction for in-switch applications. Essentially, RedPlane provides in-switch applications with one big fault-tolerant switch abstraction by offering APIs that allow developers to easily enable RedPlane in their applications, providing a protocol that correctly replicates the state entirely in the data plane, and leveraging an inexpensive replicated state store implemented on commodity servers. Now, let's take a look at key design components of RedPlane. To use RedPlane, developers implement their apps with RedPlane APIs in P4, then they compile it with a vendor-specific P4 compiler and load it to the ASIC. At runtime, while the app running on the ASIC processes packets as usual, RedPlane allows it to replicate the updated state to the external state store. While this idea of replicating state to the external state store in the data plane sounds simple, we had to address several challenges to realize our approach. First, it is challenging to correctly replicate the state entirely in the data plane. To explain this, let me use a strawman where we adapt the strict correctness used by server-based replicated systems, which typically consists of exactly one semantics and linearizability. To achieve it for every state update, the switch needs to buffer output packets until the state is successfully replicated, and the replication messages must be delivered in order and reliably. However, in today's switch data plane, it is very expensive or infeasible to implement such functionality. So our question is, what's the right definition of the correctness for in-switch applications? And is it possible to realize a correct replication without high switch resource overhead in the data plane? Fortunately, we observed that network applications are already tolerate to some amount of packet losses. So even if some input or output packets are lost during failover or due to our protocol, from end-to-end applications point of view, there's no difference from packet losses that occur without RedPlane. Based on this observation, we define a correctness model for in-switch applications named linearizable mode, which explicitly permits some input or output packet losses, but still requires in-order and reliable message delivery to guarantee linearizability. Now, let me show you how the RedPlane protocol realizes the linearizable mode. I'm going to use a per flow packet counter as an example. When a packet comes into the RedPlane switch and there's no state for the flow yet, the RedPlane runtime requests state initialization to the state store. To release an output packet only after the successful replication, instead of buffering packets locally at the switch, which is expensive or infeasible, our runtime piggybacks the output packet to the request packet. Then the state store initializes the state for the flow and sends an ACK back to the switch. Upon receiving an ACK, the switch runtime initializes the local state. Then it requests the replication to replicate the updated counter value. Upon receiving an ACK for the replication request, the RedPlane switch runtime releases the output packet. While this basic protocol seems working, there's a potential inconsistency issue due to an unreliable communication channel between a switch and the state store. More concretely, as shown in this example, the request packet loss can lead to inconsistency between the state on the switch and the state store. Packet reordering can cause a similar issue. You could think of implementing and using reliable transport such as TCP between a switch and the state store, but it's infeasible to implement such a complex full-fledged protocol in the switch data plane due to various hardware constraints. Instead of building a full-fledged reliable transport, we build a simple UDP-based transport that supports the message sequencing and lightweight retransmission. With the message sequencing, when the RedPlane runtime sends a replication request, it puts a monotonically increasing sequence number to the request. And then the state store accepts and commits the request only if the sequence number is larger than the previously committed one. To deal with possible request losses, the RedPlane runtime buffers only replication header which is only a few tens of bytes, by leveraging packet mirroring and truncating features in the switch ASICs. Even if we could correctly replicate the state for an app running on a single switch, there's another challenge when multiple switches are involved. When a switch fails or is being recovered, existing routing policy can route packets to an arbitrary switch, which may be unpredictable. In this example, the upstream switch initially routes the red flow to the switch 1. And when the switch 1 fails, it starts routing packets to another switch, which is switch 2. But we don't know if the flow will be rerouted through switch 2 or 3 in advance. In such a case, what we need to ensure is that the packet must be able to access the correct state, irrespective of the location of the current switch. Otherwise, we can face a potential problem where a packet may access a stale state. In this example with two switches, suppose that the switch 1 fails due to a link failure, so its state is still alive. In the meantime, packets in the flow are processed and state is replicated by the switch 2. Now, the switch 1 gets recovered and subsequent packets are routed to the switch 1. Since the switch 1 has the state for the flow, the packets can just read the stale state, which is incorrect. Here, the root cause is that during a transient period, multiple switches can process packets and access state for the same flow. To address this problem, we design a lease-based state ownership management that ensures only one switch processes packets for a given flow at a time. In this example, while the switch 1 is down, the switch 2 has a lease for the red flow. When the switch 1 gets recovered and if its lease has expired, it first requests a lease to obtain an ownership of the flow state, even if it has the state locally. Once it obtains the lease with the latest state for the flow, the switch 1 can now own the state and safely update and read the local state. This way, we can ensure that only one switch can process packets for a flow at a time with the latest state. And the last challenge is to deal with high traffic rate of the switch. Since the switch data plane can operate at up to a few billion packets per second, if every packet needs to access the state store, it can not only degrade the application's performance, but also exceeds the state store's processing capacity, which is typically much lower than the switch's capacity. Here, I briefly describe our key ideas for this. Our lease-based state management enables safe local reads, so if a packet does not update the state, then it does not need to access the state store. Our bounded inconsistency mode reduces the amount of state accesses for write-centric applications. Putting pieces all together, RedPlane provides a fault-tolerant state store abstraction to in-switch applications with 4 key ideas. Based on our understanding of various types of applications, we first defined linearizability-based practical correctness for in-switch applications, and provide bounded inconsistency mode for write-centric applications for better performance. And our sequencing and light rate retransmission mechanisms realize our correctness model in the switch data plane. Lastly, our lease-based state management guarantees correctness even when multiple switches are involved during failover or recovery. And it also allows local reads for better performance. Let me close with our implementation and a few performance results of RedPlane. We implemented RedPlane API and runtime as modules in P4, and using the API, we implemented in-switch applications including canonical network functions. We also implemented replicated state store running on servers in C++. We evaluated RedPlane using a testbed consisting of 2 Tofino-based programmable switches, 4 regular switches, and 10 servers. So how does RedPlane affect application latency? To understand the performance implication of RedPlane under failure-free operation, We measure per packet processing latency of NAT that is implemented either on switches or on servers and with and without fault-tolerant support. Here, this graph shows the CDF of the latency for 3 different approaches. The x-axis is log-scaled. Compared to the in-switch NAT without fault tolerance, RedPlane-enabled NAT shows the same median latency with a slightly longer tail latency due to the state initialization overhead. Compared to the server-based implementation, there is an obvious benefit of more than 6 times shorter median latency and 4 times shorter 99th percentile tail latency. And then we measure the bandwidth overhead that RedPlane protocol incurs. This graph shows the ratio of bandwidth consumed by RedPlane protocol messages to the total amount of traffic that each application processes. We can see that for read-centric applications, including NAT, firewall, and load balancer, there is almost no bandwidth overhead since RedPlane generates protocol messages only for the first packet of each flow. The serving gateway, or SGW, in LTE network, which is a mixed read and write workload, RedPlane incurs around 12% of overhead since it generates protocol messages for signaling packets in LTE networks. The synchronous counter shows the worst-case scenario where it shows the highest overhead. This result implies that in an extreme case where an application needs to replicate state synchronously for every packet, achieving fault tolerance is expensive. Then how fast the end-to-end connectivity can be recovered with RedPlane? Here we use NAT as an example, and iPerf to generate end-to-end TCP workload. Without failure, the end-to-end throughput is around 80 gigabit per second. When switch 1 fails without RedPlane, packets are rerouted to another switch, but dropped since there is no state for the flow, breaking the TCP connections. In contrast, RedPlane-enabled NAT successfully maintains high throughput when the switch fails and recovers after short disruption, which is less than a second. This recovery time is affected by both an upstream switch's failure detection and rerouting time, and RedPlane's lease period, which is configured to 1 second in this experiment. In our paper, we also have other evaluation results, including the throughput of RedPlane-enabled applications and switch resource overhead of the RedPlane protocol. We also show the correctness of our protocol using model checking. So please refer to our paper for more details. We believe that RedPlane is really the first step towards enabling highly available in-switch applications. So there are many interesting future research directions that we can build on top of RedPlane to address some limitations in the current design. A seemingly obvious next step would be supporting applications or workload types that RedPlane currently does not support very well, such as write-centric applications and applications with non-partitionable state. Also, while RedPlane provides developers with P4 APIs so that they can make their apps fault-tolerant, it would be great if we can automate this process with the compiler or language support. Lastly, designing next-generation switch architectures that enable some of the techniques we developed in RedPlane as built-in features would be an interesting direction. To conclude the talk, switch failures can affect the correctness of stateful in-switch applications. To solve this problem, today I introduced RedPlane that provides a fault-tolerant state store abstraction with 4 key ideas. Our evaluation shows that it provides a fault tolerance with minimal performance and resource overheads. Please check out our paper and GitHub repo for more details. Thank you for listening.